right, let's go through polar. Polar takes a little bit of a different mindset because we are very used to measuring distance from a point on the graph straight down to the x-axis. And a polar always measures distance from a point on the function back to the origin. So distance is always measured differently. We define it in terms of our radius. So it was always defined in terms of f of theta. So you would need to know what's my theta and how far away from that is the origin. Not how far is it away from the x-axis, but how far is that point from the origin. Usually when we're doing calculus, if you're doing derivatives and antiderivatives in polar, you want to convert. So you're going to take your r and you're going to times it by cos theta. And that will give you the x value. So if you are trying to find dx d theta, you want to create your r combined with cos theta. That had to do with SOHCAHTOA trig. Do you remember what it was for y? Okay, that would be r sine theta. So then when you took your derivatives, dx d theta would always be then the derivative of those things. So you would apply the derivative rules, which often took a product rule and a chain rule. Okay, so you're going to have to do product and chain. Same thing with your dy d theta. You would have to do a product and a chain rule because it's r times. So you're going to have to do a little bit of work to figure out. Then we have area. Okay, so if you're thinking about area, area is always swept out in what we call a sector. And so the area would be between two of those angles. So any two given angles, you're going to figure out the area in between. Sometimes it's a nice circle, but a lot of times that radius is wavy and you're trying to figure out, oh, it's loopy all over the place. So the area is going to go from, theta 1 to theta 2. So maybe it'll be from 0 to pi halves, or it's from two different radian measures. Okay. And then do you remember how to do the area? It's got a half. It's not the square root. Okay, so it's just r squared if we're doing it between two angles of a polar function. All right, so it'll be 1/2 times whatever r is squared. Now, I think you were thinking about two different polar functions. So if you have an outer polar function and you have an inner polar function, I think that's what you're thinking of. And so if we have that from theta 1 to theta 2, that would be 1/2, and then you'd have like an r squared 1 minus an r squared sub 2. And that's d theta as well. So that'll be the outer radius and then minus the inner radius. But it's the same, the angles that are shared. So what if the shape of the outer rose or daisy or whatever you're getting, what if it crosses and it was the outer and then it crosses to the inner? You got to break your integral up, right? And so wherever they're going to cross, that's going to create a new integral, and then you're going to switch them around. So let's just do a couple samples. So find the slope of the polar curve. So if we're going to do the slope of the polar curve, we need to know what dx d theta and dy d theta are, so that then we can figure out what dy dx is. So first you want to go with dx d theta. Actually, first you want to create x. Let's do that first. So x is going to be r times cos theta. So in this case, r is 2 sine 3 theta. But I need to multiply that by cos theta. So you see you end up with a product. So in order to find your dx d theta, you're going to need the product rule, and you're going to need the chain rule because I've got the 3 inside the parentheses, so I'm going to have a combo of those things going on. So I'll have dx d theta. So that'll be the product rule, says start with cos theta and then multiply by 2 cos 3 theta times 3. So that's the first part of the product rule. And then plus, then you do the second part of your product rule. So 2 sine 3 theta times negative sine theta. And then you can plug pi sixths into that to evaluate. So that'll give me cos of pi sixths times 6 cos of pi halves, and then 2 sine of pi halves times the negative sine of pi sixths. So it just becomes, okay, now it's back to just being a trig problem. So the cosine of pi sixths, okay, that'll be rad 3 over 2. The cosine of pi halves is 0. So great, this whole part right here is all going to be 0. And then the sine of pi halves is 1. And the sine of pi sixths is 1/2. So all that simplifies down to 2 times negative half, or negative 1. So that's my dx d theta. Okay, then you want to do your dy d theta. So again, it's just a matter of making the equation. So I'll have 2 sine 3 theta this time times sine of theta. So my product rule is going to be similar with just that little variation of having a different product. So dy d theta, okay, you work your way through the product rule for that. I like to start with sine of theta, and then I'll have 2 cos 3 theta times 3 plus, I'll have my 2 sine 3 theta times cos theta, and then evaluating that at pi sixths. So sine of pi sixths, and then 6 times the cosine of pi halves. Again, I'll get 0 there. And then 2 sine of pi halves times cosine of pi sixths. So one more time I get 0 for that whole first part. And then 2 times the sine of pi halves is 1 again. So I have 2 times 1 times rad 3 over 2. So that works out to be rad 3. All right, so I have dx d theta and I have dy d theta, but I haven't yet answered the question. And the question is to find the slope. So I'll need to take a combination of those two things to figure out what dy dx is. So my final answer here is going to be, if you've got room somewhere, the slope will be dy d theta over dx d theta. So that would be rad 3 over, I already forgot what dx d theta was, negative 1. So negative rad 3. Any questions on that one? Okay, and the last one we'll just do is to find an area inside of a circle but outside of a cardioid. You will not have to create these graphs by hand. You'll either get a picture that's given to you, or you'll have your calculator to graph it. All right, now a circle of radius 1, everybody should know circle of radius 1, right? So we just have our straight out circle of radius 1. Okay, but the cardioid, This is going to be a circle that's been moved along the x-axis and creating a little, looks kind of like a sideways heart, sort of. And so you would go ahead and practice that. Grab your calculator, set it to make sure you're in radian mode. And then also make sure you're in polar mode. And then when you do your, we don't have any bounds here yet. So make sure your bounds are 0 to 2 pi so that you cover and you can see the whole window. Polar mode, yep. So your window should have 0 to 2 pi for your theta with a pretty small step. Your x's, I would, maybe do -5 to 5 or -3 to 3, just because we know, we're talking about a radius of 1, so it's not like this is going to be gigantic. So I end up with a graph that looked like this. That was mine. Okay, so I want inside the circle, but outside the cardioid. Okay, inside the circle, but outside the cardioid. So we are looking at this area. So let's set up our integral. What quadrants is this in? 1 and 4, okay. So then what would my bounds be if I was setting up my area? Yeah, to cover, so she said -pi-halves to pi-halves. That would cover all of quadrant 4 and all of quadrant 1. Is there another way you could do it? 0 to pi-halves and then double it? That's probably what I would do, is I would say you could either go -pi-halves to +pi-halves, but my tendency is to try and use 0 whenever I can. So I would use 0 and then just make sure I'm doubling that. Okay, and then I'll have 1/2. Then I'll have the outer radius, which is being formed by the circle. And so that would be 1 squared minus, and then the inner radius is following the cardioid. So that's 1 minus cos theta, and that quantity is squared. Okay, so that's setting it up, and the rest is just using your calculator to evaluate that on the Math 9. All right, seems like we're all getting 1.2146 or 1.215.